Well, good afternoon, and thank you very much for this honor of speaking on the occasion of Lakshmi Raman Memorial Lecture, and a special thanks to her family for setting up this lecture series, and to you all for inviting me to come and talk to you on this occasion. So I want to first of all say, do interrupt if you have questions. And this is a colloquium, so I want to give you some flavor of some rather unusual world that we can access in quantum matter. So, and that unusual world will come alive, I hope, as we go on. So, let's start with the universe. We all love to look at the sky, the universe with our eyes, with telescopes, and this wonder never leaves us. But let's look at the other direction, at a black pellet. You might be walking around, find a black pellet, and you generally kick it off. It's just a boring stone. But who knows what's inside that black pellet? You need tools, just like you need telescopes, you need correspondingly microscopes and other tools to look inside. And sometimes, not always, sometimes they really are boring stones, but sometimes new worlds can appear. And that is the part of the story I want to tell you about. And rather remarkably, in our research, we are even finding, by we, I mean collectively, collectively scientists are finding that there are connections now between black holes and some of these quantum worlds. So I have to use two of these, one to change, one for the green light. So let's see. Okay, so that's the big story I want to tell you. But let's start with something really simple. So what I've shown here is, say, a typical measurement you might be doing, some of you might be doing in your labs. You have some material, and you are measuring its magnetic properties. The magnetic properties, the magnetization changes with temperature. Typically when you have these spins or local moments at low temperatures, the entropy is reduced because the thermal energy is going down, and so the entropy is small, the spins are aligned. As you raise the temperature, they get disordered. So you go from an ordered magnet to a disordered paramagnet. That's a phase transition. And I think you've all seen this in some of your classes. Okay, so all I'm saying, the reason for bringing this up, I started loftily with the universe, and I want to kind of bring to bear that sometimes it's starting out with very small steps in your lab. Every day something is happening. We just have to be alert. There could be something exciting going on. And we have to be alert to finding them. So for example, this is something we all know, we understand, but a lot of beautiful physics went into understanding these phase transitions. And from this simple observation that magnetism is lost, not just gradually, it doesn't just peter away with temperature, gradually, but there's a sharp phase transition where an ordered state becomes disordered. Beautiful mathematics was developed. It's called the renormalization group theory that we use to understand this. All good. Now, I'm going to turn on another axis. It's taking this magnet and somehow interfering with the interactions. Exactly what they are, I will explain as we go along. But just imagine there is something frustrating the spins that is not allowing them to order. So what that ends up doing is that ordered magnet, now once again its magnetization is getting reduced, not due to temperature, but another parameter, which I'm calling frustration. Later on you will see this will be temperature is like a thermal fluctuation, and this frustration I will introduce will be a quantum fluctuation. It's a different type of fluctuation that will disorder the magnet, and that fluctuation again takes the ordered magnet and disorders it. So you see, we have a disordered paramagnet here, and this also is a disordered magnet. But what I'm going to show you is that this disordered magnet is a whole different world. Okay, we will see that this disordered magnet is what I will call a quantum spin liquid, and it will have some phenomenal quantum properties that don't exist in this classical disordered magnet, but do exist in this quantum disordered magnet. So that's the story I want to tell. And the reason I put this up is if you were working in a lab and just doing a simple experiment, you would indeed see your magnet is not ordering. And you may throw that away as a boring pellet, but boy, what a beautiful world will emerge from here. And that world will actually connect the mathematics with the mathematics of black holes and chaos. So let's go on. So just to make it very clear, because I said that state of matter is called a quantum spin liquid, and at this point you're probably thirsty and thinking of maybe water or maybe something else. It's Friday after all. No, is it Friday today? It's only Wednesday, sorry. I'm racing ahead. Okay, so no beer yet. But you're probably thinking of a liquid, of something flowing. And I'm going to explain what this quantum spin liquid is. It is a new state of matter, and I want to put it out here. You may have heard of many new states of matter. Magnets, they are not so new. You know, we have known about them for like millennia. Superconductors, you heard Mohit's talk yesterday, and all the beautiful superconductors we know about. This is not a new type of charge order yet, not a charge order either, yet this quantum spin liquid is exotic. And how is it exotic is what will become apparent. So let's take quantum matter, you know, and it's good to have a big picture. Where are different things fitting in? Otherwise, it looks like little pieces of information randomly blinking. So where are these different things fitting in? So quantum matter can be put on two major paradigms, the Landau paradigm and the topological paradigm. Under the Landau paradigm, that's how we understand magnets, superconductors, and so on, like crystals, even the formation of crystals. I showed you gas, as you cool it, it becomes a liquid, and then it becomes a crystal. All of these spontaneously break some kind of symmetry, either translational or rotational. And that broken symmetric state can be described by a local order parameter. So the key word here is you're describing phases here with a local order parameter. For example, a local magnetization or a local complex pairing amplitude for a superconductor. And furthermore, once you get this local order parameter and long-range order in the ground state, you can ask what are the excitations, and these excitations are bosonic. It doesn't matter whether you have a magnet or a crystal, the excitations are spin waves or lattice elastic modes. These are all bosonic excitations. They have Bose statistics. On the other hand, in the topological paradigm, the single point is that you cannot just define something locally. So the word topology signifies shapes and the genus of shapes. Is it a sphere with no holes? Is it a donut or a vada with a single hole? Or is it like multiple holes? So that's the genus. And that dictates the nature of the ground state, how many degenerate ground states you have. So that's where the topology is coming in. And even here, I have put two pathways, one which I call integer quantum Hall effect. That is a paradigmatic system where topology plays an important role. However, these systems can nevertheless be understood in terms of non-interacting electrons or non-interacting. It could be other degrees of freedom. So topology is important, but you can still describe the degrees of freedom as being non-interacting. The other prong takes us to what I call the fractional quantum Hall effect, which is a paradigmatic problem in that direction. Here, you have a particular, rather than a local order, there is something called a topological order, and this problem here cannot be understood without including strong interaction between your entities, say between electrons. And the consequence of that strong interaction is, as I was saying, you get ground state degeneracy, but other things emerge. There is long-range entanglement, which I will describe, and also something very bizarre, and that is fractionalized excitations. And quantum spin liquids falls in this pathway. So that's the first thing I wanted to say, that the story to here is really along the most exciting pathway on this quantum matter classification. Oh, I didn't mean to. Okay, so that was quantum matter, but what is exciting about these developments today is these quantum spin liquids become a platform for creating topological qubits. You must have heard about qubits. These are topologically protected qubits. Because of the role of topology and shapes, you can't upset the qubits locally. You have to make global changes to change their behavior, and that's why they become very important for quantum information. So the field today brings quantum matter and quantum information together. And of course, this is very easy to do on PowerPoint, but really the fields are coming together, and you can see that in your own department. There are activities on both sides, and there's a lot of cross discussion of ideas, which was really heartening to see. Okay, so my colloquium, I decided to kind of start with something familiar and tell you the story of quantum mechanics. And you probably heard of the story somewhere along this pathway. So I'm going to start with, let's say, one particle, which I think you all study in your quantum mechanics courses, wave-particle duality, and then go to two-particle entanglement, and then ... all the way to n-particle entanglement, which is what brings materials. Because in materials, n is like billions and billions. But this is like a log scale. There's a lot of space here for quantum information where people study few multipartite entanglement and so on. Okay, so I think you all have seen this experiment by now by Tonomura. It's a classic experiment. Well, it's a quantum experiment, classic in the sense of really important experiment, but it's a two-slit, let me start it. Yeah, so this is a two-slit experiment. Have you guys seen it on YouTube or in your classes? Yeah, I see a lot of nods. Okay, great. So the reason I'm starting with this was an important experiment that I read about when I was an undergrad at IIT Delhi. It kind of sealed my career in physics. So when you are an undergrad, you're sort of not sure what you want to, what area you want to be in, what career you want to have. And then that summer, first summer after IIT, after my semester at IIT, I was back home, and I came across Feynman's lectures, and he talks about this experiment. That experiment didn't exist at that time, but it was a Gedanken experiment. It was a thought experiment, and he beautifully describes it. Feynman is not in a rush to move on. He beautifully describes the two-slit experiment with electrons. So what is happening, as you just saw, there are two slits, so there's with two openings, and there's a single electron going through. And you saw the clicks, the random dots, seemingly random dots. Now, had these been P's, that you were shooting, they would have made just an imprint of the two slits. You would have gotten just two bright bars showing where the piece had gone through, but instead, each single electron is a wave, as you know, and that makes this beautiful interference pattern. And a decade after I graduated, this experiment was done. So when I read about that, it was just imagination. I was so intrigued that something like this could even be happening, that an electron, was a single electron was a wave. It's not like water waves, but a single electron was a wave. And I said, whatever it is, this is a subject I want to know more about, and I want this to be my field of investigation. Okay, so just a month ago, I got to go back to IIT Delhi after all this time being away and meet my professor, Ghatak, who taught me quantum mechanics and instilled that joy of that subject in me. And I got to go back and say thank you to him. So that was really, really very sweet. And I wanted to share that because, right now you're learning so many things from your teachers. I didn't even appreciate it at that time. But much later, I realized what an impact he had made. Okay, and these things have a life of their own. Thinking of Lakshmi Raman and how she impacted society, I also felt I should, do something about communicating this joy of the wave-particle duality. So we did an event at the museum in Columbus, Ohio. This title, "My Quantum Mom," comes from a remark my daughter made one day when I told her, I have to travel, and she said, couldn't you be a quantum mom and, be in two places at the same time kind of thing, how kids are. So anyway, that led to this event at the museum. So, we all share a large part of what we learn in many different ways, and I hope you take the excitement of whatever you're doing.
Not far from quantum mom, because you talked about electron wave interference. Now they have seen interference of protein molecules.
Yes, yes. Yes, yes, yes. No, bacteria. Yeah, they have seen it. Okay, so two-particle entanglement. Now, two-particle, you'll also have interference, but there's another aspect that doesn't happen with one particle, and that is entanglement. And this was first introduced by John Bell. He's the hero of quantum entanglement. In 2022, Aspe, Clauser, and Zeilinger were awarded the Nobel Prize for their experiments with two-photon entanglement. And essentially, an entangled state is a state that you cannot separate into what, let's say, electron 1 is doing and electron 2 is doing. So that's a separable state or a product state. But something like this, like a singlet, up, down, minus down, up, this is a Bell pair, and it's an entangled state. So now we are not surprised about entangled states on the scale of an atom. We see that, in helium, the two electrons form a singlet. That's an entangled state, but that's on the scale of nanometers. The Aspe experiment was on the scale of a table, so 10 meters. And it was already, what is surprising about this is if you have an entangled state and send the two electrons 10 meters apart, you measure one of them, the state of the other electron collapses instantly. Okay, so if you measure up, the other one is down. If you measure down, the other one is up. Okay, that was really amazing, and they showed that the correlations in this state are non-classical. They cannot be understood by just classical physics and concocting any kind of hidden variable theories. But what got everybody's attention was the 2017 experiment by the Chinese group, and they were able to show entangled photons over 1,200 kilometers. Now everybody sat up that this is now a reality. It can be used for, so quantum information at that point got the attention of the politicians, let's say, and the people in industry. Scientists were excited just with the 10-meter experiment. That already proved the principle. But the other one caught everyone's attention. Okay, so now marching on to n particle entanglement, where n is large. And you might ask, okay, what does this enable, having many, many more qubits entangled? And that state I call a quantum spin liquid. And what it brings forward, I'm just showing you in a little cartoon, but this contains the essence of the ideas. So you have to just understand how profound the consequences of entanglement with many qubits is. So if you think of an electron, it has charge and spin, and it's a fundamental particle, right? So in vacuum, that's what an electron is. Charge and spin tied together, a fundamental particle. But in a material that we call a Mott insulator, this is an insulator not like silicon. It's driven insulating due to correlations. The electron charge and spin can separate. And that means you can have, as far as the charge is concerned, you can have an insulator. But as far as spin is concerned, so insulator means no charge excitations until you reach at energies larger than a gap. But if you look at spin excitations, there are low energy spin excitations. So the spin and charge have separated. In a spin liquid, you get the next level of fractionalization also. So the spin now further fractionalizes into, I call them anions. And these are these four different colors here. But they fractionalize into anions. And this, again, to emphasize, would not happen in vacuum. It can only happen in a multi-qubit system where they are highly entangled. Okay, so we have quite a job before us. We have to, if you're a theorist, you want to find models where you can find such phenomena. And then you want to interact with your experimental colleagues and see if you can find materials where you can find such states of matter and detect these fractionalized excitations. And moreover, detect these excitations with a sharp signature. Not just that I see a signature which is essentially lack of any magnetic ordering. That's a first step, but we would like some sharp signature. So that's the charge before us. So we want to understand, it would be great if we could have more dialogue, but I'm going to go on just to see what kind of questions come up. So we want to understand, why does a spin fractionalize? What causes that? Yeah. Yeah, it's just you create them. You can create. So here, you create. Let's say in a lab, right? So they are on your lab scale. But then the two photons can be sent off to large distances, and that is where the distance is coming on. It's not that you are creating them at large distances. You're creating them in your lab on some small scale, but then you're sending the photons off. And they remain entangled at that distance. Okay, so we want to understand, why does a spin fractionalize? Where can I see this? What is the signature I should look for? And also at the end of the day, why are they useful? So I won't say much about why are they useful. That takes us toward topological quantum computing. It's a whole other talk, but at least the first three we can try to get through. Okay, so before I get into these anions, I want to quickly show a cartoon about something you are more familiar with, which is fermions and bosons, right? So so all the particles, so high energy physicists will tell you about many, many particles. Doesn't matter what their names are, there are only two categories. Either they are integer spin or half integer spin. If they are integer spin, let's do that first because your guest house is named after bosons. So if they are integer spins, all the bosons, they are the happy-go-lucky ones. They all like to, as you lower the temperature, all collect in one single state. That's the Bose-Einstein condensation. If they are half integer, not integer spins, but half integer, then they have a Pauli exclusion principle, and you can't have two fermions in the same state, so you need a certain number of states to fill these fermions that you have, and that defines a Fermi energy. So these are the more individual guys. Okay, now this is a quick, I'm quickly showing you these experiments which have become possible. So I've been usually talking about materials, but another system that we often connect with are cold atoms. These are neutral atoms, and you can give even neutral atoms a statistic. So in high energy physics, the energy is so high that you're breaking an atom up. So you're looking at statistics of separately of protons and neutrons, and if you break those further, you're going into quarks and so on. But now I'm coming in with low energies, so I'm not breaking up these atoms. So even composite atoms have a statistic. Masses like smaller de Broglie wavelength than an electron, but if you cool them, the can overlap, and that can give us their statistics. So that is what has happened here. This is lithium-7, lithium-6. Everything is the same except lithium-7 has one more neutron than lithium-6. And so this is even number, this is odd number. A neutron by itself is a fermion, but lithium-7, because it has 4 neutrons, becomes boson. And you can see as you cool it, the size of this cloud is a measure of the number of states that are being used to fill the bosons. So as you cool it, they're getting scrunched further and further. This is still not 0, so otherwise it would have been a single dot, but it's going toward all the bosons condensing in one state. Lithium-6, on the other hand, the cloud size stops shrinking, and that's the pressure of the fermions that is being exerted, because beyond a point, you just can't shrink the cloud. So this is a beautiful experiment that has now become possible with cold atoms. Now, pardon? The coordinates. This is so what they do is they create the cloud in a small trap, magnetic trap, and then they let the trap, the magnetic trap, they send it to 0, the magnetic trap. The cloud expands. So this is a measure of the energy of the cloud. Okay, the size of the cloud that you are seeing, the XY, it's a real space image of the size of the cloud. And if the cloud is very big, that means it has used a number of states to fill the particles you have. So the shrinking of the cloud is telling you how many states are being used to fill the particles. Is that clear? Okay. Okay, now anyons. What are anyons? I talked about bosons and fermions in 2 dimensions. You can also have anyons, and they can be seen in these quantum Hall states. I'm not going into this because this is a whole other talk, but just to say that this is really the most clean system where a number of these a number of these fascinating states have been observed. And let me just show this very quickly. If you haven't seen this behavior before, maybe you can check out some of the references online about it. But essentially, this is a 2-dimensional electron gas. It's not a complicated material. You apply a magnetic field, and it gives you the Hall resistance. You see certain plateaus, and correspondingly, the longitudinal resistance shows some dips here. And these plateaus occur in units of h/e², at integer values, that's the integer quantum Hall effect that you can understand in terms of electrons. But once you get a fractional plateau at a filling of 1/3 of a Landau level, this feature you cannot understand in terms of electrons. It's the understanding of that is that the electron has fractionalized into 3 pieces. And those fractions are responsible for the emergent state that gives you this plateau. Now, again, look at the dates here. This is 82, this is 2000. The samples improved, and with that, many, many more features have been observed. And the reason I like to show that is very often when the first experiment is done, there are a lot of criticisms about, the data. But we just have to be patient and really improve the quality of materials to start to see all the beauty that is there but has to be revealed. So quantum spin liquids right now is in this kind of a state. People are finding materials, and the experiments are just starting to happen, and they are revealing some interesting things, but we still need a lot of progress to get from here to here. But we are starting to see features in materials at this level. Yeah.
Just a clarifying question. So, when you say quantum spin liquids, does it necessarily mean that there are fractional excitations around? Or can you have quantum spin liquids with no fractional excitations?
No, it necessarily means you'll have. Yeah, and you'll see why. Okay. So let's get into that. Can we get such states of matter in quantum materials? And the answer is in these kind of materials. So first thing is you want to so just to again reiterate, what is now I'm coming into materials. So what we have is a magnetic material. It has local moments, like each of you could be a spin. And you're lowering the temperature. Typically, these local moments, they interact with their neighbors. So these interactions would have forced some kind of order, but they don't order. Okay, so that's the first puzzle. Why are they not ordering? And very quickly, I'll give you an energetic reason. So let's say I have some Hamiltonian with, this is a Heisenberg Hamiltonian with spin-spin interactions. And this coupling is positive, which means the spins want to anti-align. So here it is. The spins are anti-aligned, up and down. And that gives me an energy of -1/4. These are spin half qubits. Okay, now look at this Hamiltonian. Just up and down is not an eigenstate of this Hamiltonian because it also has the XX and YY components. And those components don't all commute. So that's the crucial thing. Your Hamiltonian has a classical piece and another piece in the Hamiltonian that doesn't commute. This should be a product here. So because of the two pieces not commuting, the classical state cannot be an eigenstate of the Hamiltonian, and the additional terms cause quantum fluctuations. That's what we mean by quantum fluctuations. It's non-commuting terms that perturb the classical solution. So what you have is this XY terms which take a down-up and flip it to up-down. And as a result, if you include these pieces, you can show that a singlet has a lower energy. Instead of a -1/4, you get -3/4. So you can see by including quantum fluctuations, you are basically reducing the energy, but at a cost of upsetting the nice order. This is with just 2 spins, but if you had more spins, they would have been, the classical state would have been up, down, beautifully ordered, or it could have been down, up. So that's just a twofold symmetry, but the quantum fluctuations are putting in, mixing in other configurations which are lowering the order, but removing the order, but doing it because it's energetically favorable. Okay, so yes. Yes.
whereas the fluctuations is actually leading to entanglement.
Yes.
Or you could also have a situation where it's the other way around, maybe, where you have the ground state, which is in fact unentangled, and
Unentangled.
yeah, unentangled classical, and the excited states are entangled with your fluctuations. I mean,
Yeah, so
of terminology,
no,
because you're
no,
moving from temperature and so on.
no. It's not a question of terminology. I'll explain it. Let's see, do I have? Yeah, maybe just I'll show you a picture which will make this clear. So let's have a picture of a quantum spin liquid, right? That's important. So if I have two spins, a singlet is, I'm going to represent this singlet with a circle. Now let's take 6 spins, right? So I can make different states. They could be these 1 and 2 are entangled, 2 and 3, and so on. I can make another picture of this entangled state by making these 1 and 3 and so on. This is another picture of how the 6 spins could get could form singlets. And here's another one. So in a spin liquid, this is the difference with what you were asking. So if I had thermal fluctuations, right? What does temperature do? If you have, let's say, n qubits, you have 2 to the n configurations. And at a given temperature, all of these configurations will contribute with some probability, right? Here, I'm looking at the ground state, not the excited states. Now I'm asking about the ground state. The ground state has contributions from several configurations because it lowers the energy, and they can come with different coefficients, but this soup of singlets is a picture of what a spin liquid looks like. Does that answer your question? Because now they are coming in with amplitudes, and these amplitudes will describe a wave function rather than probabilities.
I think my question was more like, the word fluctuations.
Ah.
Is that something which is a hangover from the temperature side of things? Because if you lower the temperature, you would go to something which is ordered. Here you have to probably turn off what you're calling frustration. But what you're calling frustration is basically quantum.
So no, the distinction is they are very different. Okay, let me explain again why. Yeah. Oh, the word. Yeah, the use of the word. Yes.
It's like, there is something steady and then
Yeah.
something fluctuating.
So the use of the word fluctuation is relative to the classical state. Okay? So the classical state is, let's say, an antiferromagnetic state. But that is not an eigenstate of the Hamiltonian. So the word fluctuation is being used to say that additional configurations are being mixed in to the classical state to produce the quantum state. So in the quantum state, the system is dynamically accessing several configurations, whereas the classical state would have been static. Now, temperature is also going to make your system fluctuate between different states, but that will be accessing with different probabilities. Here it will access the wave function with different amplitudes. So that fluctuation. So yes, one axis, so what is happening here is you are at 0 temperature, so the thermal fluctuations don't play a role. So entropy doesn't play a role. So usually we are we are minimizing the free energy. Here we are at 0 temperature, we are minimizing the energy, and the key point is the energy is minimized by including several configurations, and that's the fluctuations that are being added into the classical state. Okay, great. So if you have this, now you can see the key ingredient is that this state is highly entangled. So that's the one thing we find, one thing you can see. And the other point that was raised is, will it always have fractionalized excitation? So let's look at this. Again, I'll show it pictorially. So this is a essentially have now gone to 2 dimensions. The earlier picture was in 1D, but 2D is important because you want to create excitations and braid them, and you can't braid them in 1 dimension. So quantum spin liquids should really be discussed in 2 dimensions. And what you see here are a bunch of singlets that I have now broken one of the singlets. So you're essentially looking at a spin 1 excitation. So let me explain what I mean there. So let's say all the spins were up. This is spin half. If I flip one of them, I change my spin. It go from half to minus half. So that's delta S of minus 1, right? So it's a bosonic excitation. So let's do a delta S equal to 1 excitation. Now what happens here is you basically have created 2 quasi-particles with spin half, and these are called spin-ons. Bhaskaran was telling me the other day, this is a word he coined in one of the early papers. And so you've created these 2 spin-ons, 2 spin-half excitations that are neutral. They don't have charge, and they can be moved further and further apart because you can rearrange these configurations. Since the ground state has a linear superposition of all of these configurations, you can basically take these 2 spin-ons which were nearby and move them extremely far apart so they can get deconfined. And that is the way you can get essentially fractionalized excitations in this picture. Now you might ask, how would we see these fractionalized excitations? So this is a very quick repeat of what I just said. You've flipped a spin, and typically when you flip a spin in an ordered magnet, right, you can do 2 experiments, one in an ordered magnet, one in this highly entangled state. So if you do these 2 experiments, so in an ordered magnet, this spin 1 excitation essentially moves as a spin wave. That's what I've shown here. I've made a spin wave which has the same angular momentum with the rather than making an abrupt spin flip, you can create lower energy excitations which have these slow moving, slowly tilting waves. These are called spin waves or magnons. And the signature of that in an experiment, so you can use neutrons to probe your system. And what do? You come in with neutrons with some energy, momentum, and some spin of the neutron, scatter into E prime, K prime, and a different spin if you want for the neutron. And the difference is dumped into the system, and that leads to some excitation of the system, which can be observed at the detector. So as you are scanning your energy of the input neutrons, at the resonant energy where you can make magnon excitations, you get sharp peaks in energy and momentum. So that's how these excitations are typically observed in an ordered magnet. So let's look at some data. So here is the data for a typical, this is one of the high temperature superconducting parent materials that has long range antiferromagnetic order, and in such a case you indeed see very sharp peaks. And if you try to make a map of what is the energy and momentum of these sharp peaks, they have this kind of a dispersion. In another material, this is now a spin liquid candidate material, ruthenium trichloride. I may have more to say about that. But the same picture that you see here, which was sharp modes, it doesn't look like that at all. It's like somebody came and washed up all the structure. It's completely featureless, and that is the first signature that you have something fractionalizing. Why? Because if your spin 1 excitation breaks up into 2 spin half excitations, what you have, the energy and momentum that was dumped into the system can be shared in many ways between 2 of these spin-ons, right? And if you can share any energy and momentum in multiple ways, then it's going to be broad in momentum and energy. So that's the map that you get for a spin liquid. And it's a very clear signature that you have something fractionalized. Of course, you have to make sure that disorder and other things are not being implicated. Okay, so I'm going to kind of, stop here for a brief moment, just at this point, because I've shown you that a spin liquid has no long-range order, but yet it is not like a boring paramagnet. It is a quantum paramagnet with long-range patterns of entanglement and fractionalized anions. Okay, I still have more to say, but let's see if there are any questions here. Yeah.
What you seem to be suggesting that just from a purely quantum information theoretic point of view, this looks like a very elegant way to even detect entanglement. Like I don't have to do full state quantum tomography and things like that, but still I am.
Yeah. I would not call it a sharp signature yet, but you can go, what I will end with was, this was a spectrum of a single spin flip. This is already broad. It's not a full state tomography by any means, but you can do the next level, which is 2 spin flip, and that already has a huge amount of signature. So that would be one important message, that instead of a full state tomography, doing at least a 2 spin flip gives you sharp signatures, where the single spin is broad. Yeah. Thanks for that question.
I just wanted to clarify. So the term with the non-commuting operators, you could tune it to change the extent of entanglement?
Yes, yes. So, I had a interaction coefficient which was J, and it was the same strength for the Ising piece and the XY piece, right? So they were mixing, the quantum fluctuations were of the same strength, but you could relatively tune it. Yeah. And in real materials, they do occur with different, you can have anisotropic interactions. You can also have other terms. Yes.
I have a question. Maybe I haven't understood this fractional excitation theory. So suppose I have a group pair, it's in the single, and an excitation would be to break the pair, and then I have two spin half.
Triplet.
Yeah, it's in the triplet, but it's still 2 spin halves, right? So can't I do the same thing here? So what is fractionalization?
So the excitation would be a spin 1. They would be bosonic. Now, those are not, when we talk about an excitation, it's a mode. It's something sharp, right? So that mode is no longer a propagating mode, but it has split up into some fractions, and those are now the deconfined modes. Okay, maybe it'll become clearer as I show you a specific model. Okay.
If I compute the entanglement entropy,
Yeah.
then this is always going to be log in 2D,
Always going to be?
area law with the prefactor.
Yeah, yeah. I haven't come to that, but yes, that's what it'll be. Okay, let me, yeah, sorry. Yes. So, we are discussing detecting these states, and noise, looking at fluctuations is in a correlated way. So, people look at noise, like that is how they saw the 1/3 charge of the fractional quantum effect. It's a beautiful experiment using noise. It's like hailstorm on your rooftop. If you want to know what is the size of the hailstorm, you're hearing the sound, tut, 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 tut. If it's a tiny particle, you can quantify that noise, and whether it's charge E or charge E over 3. And that's how the 1/3 charge was observed. Now here, you don't want to just do a single point noise, but a correlated noise between 2 points to see the entanglement, and thereby see the cross correlations, the coincidence. So that is another proposed experiment which hasn't been done. Okay, now what I want to do, I know I have should be stopping very soon, but let me just give you a little idea of how this field has evolved. So if you got this much, that's actually a good big picture to carry forward. But there have been some really important developments in the field, and one key development was by Kitaev. And what he was able to show is for a two-dimensional model, he was able to show that this state, that the ground state has no long-range order. It has long-range patterns of entanglement, and it has topological order, which he obtained from the entanglement entropy. So that is a very key result, because if you can prove that there is a Hamiltonian which has a spin liquid, then at least we know they exist. Because until this work, there were many proposals, but in the absence of a proof, it was never clear if various models that people wrote down, if the result was a consequence of approximations, which you have to make in order to solve the problem, or what the state. So let me just very quickly tell you how this has elements of what I have been talking about and what exactly is frustration. You'll see it here. So this is a model on a honeycomb lattice, and at every point there's a at every site of this honeycomb there's a qubit. Now these qubits don't interact the way I wrote earlier, S dot S or sigma dot sigma with all the components on every bond, but they have bond-specific interactions. So on the blue bond, only the X components interact. Green bond, Y components, red bond, Z component. And as I said, these three Pauli matrices don't commute. So now, I'm not going into the details of the method, but essentially he fractionalized this spin into anyons that I was talking about. Okay, so that's where the fractionalization happened. And after he fractionalized it, this model has some conserved quantities. In terms of those conserved sectors, it was possible to write get a quadratic Hamiltonian that you could then diagonalize. As you know, if you have a quadratic problem, you know its exact solution. So here, it's not a quadratic problem, because these are in terms of fermions, they have 4 fermion terms, but once you do this parton construction, parton means you break it into parts, then it becomes a quadratic problem. And in this specific case, you know, these fermions, these broken up partons, are actually a particular fermion that is its own antiparticle, also called a Majorana. Okay, so this is the result. So this is the key point. The exact solution says it doesn't have long-range order, and it is a spin liquid with long-range entanglement. So where are the elements coming in? So first, if you know, this looks like a nice bipartite lattice, but if you look at a particular qubit, the frustration is coming in because the 3 interactions on the bonds, X, Y, and Z bonds, are giving 3 totally competing instructions to the single qubit in the center, telling it to order along X, Y, or Z. So it's frustrated. You know, your teachers tell you something, your parents tell you something, your children tell you something, a third instruction you've given up. You're like, whoa, I have no idea what to do. So that's the frustration. That's why this qubit cannot order. So now what does it do? It could just remain there and just throw up its hands, but no, that's where you know, matter is just so ingenious. It breaks up into 4 parts. Okay, now just look at the beauty of the solution. It has broken up into 4 anions, and they've been color-coded. So the blue joins the blue, the green, and so on. And before you know it, you have a plaquette operator here. As you go around a plaquette, you pick up a magnetic field, right? So A dot dl, that's a magnetic field. You remember that from your EM. So now here, there's no magnetic field that is being applied. It's emergent. Right? It's emergent because of the strong interactions. This is the gauge theory that is emergent, and that's the magnetic field. So there's fractionalization and emergence of 2 new degrees of freedom, fluxes and these itinerant Majoranas. These black ones are now itinerant. So before, nothing was moving. The spins were localized on sites, right? Now the spin has fractionalized, one set became fluxes, and one of them, the black one, can move. And when I say move, that degree of freedom disperses on a honeycomb lattice. It is like a graphene problem. Graphene has a honeycomb lattice. So it's like a Majorana, itinerant Majorana, that's the black one, in a background of fluxes. And so what you get is an emergent gauge theory and fractionalized matter. So that is the reason, no matter what kind of spin liquid you have, these are the features it will have. Frustration, new degrees of freedom, and then emergence of fractionalization and new degrees of freedom. The gauge theories will be different depending on the details, but you must have these elements. Okay, so now I'm going to skip a lot of these things and just end by a couple of predictions of this. So and also kind of touch a little bit on work in my group. Where have we taken this? So Kitaev had this exact solution. And what he was able to show was there were these flux sectors where the ground state had no flux, and there were these itinerant Majoranas. And that was a spin liquid. And what we were able to do, let me just quickly show you our result. What we were able to do was apply a field, not just perturbatively. So we took the exact solution and we said, where can we go with it? Now we use numerical methods of different kinds. And we decided to use it on this problem because we have an anchor point. We know one point where there's an exact solution. So we decided to add a magnetic field. Okay, now in the beginning, this is another fun part of research and discovery. We really didn't know what to expect because the single thing we were expecting is you have a spin liquid, you add a magnetic field, all the spins are going to get polarized, right? That's what happen. The spins will align with the magnetic field and you will get a polarized state. But something strange happened. So this was the state that we had, that you get at, so you're starting with a Kitaev spin liquid here, which is actually, I have to tell you one more thing. Okay, so you're starting with a Kitaev spin liquid here where the Majoranas are forming a Dirac spectrum on this honeycomb lattice. It opens a small gap as you turn on a field, that's perturbatively, and you may think at some point here there would be a transition to a polarized phase. Now look what we found. We were looking at the spectrum, and instead of this gap, you expect this gap to be growing. Instead of the gap just growing, we found the gap coming down at some point, and then a large number of states came down in energy and remained gapless for a range of fields, and then you got into the polarized phase. So this was an indication that between the spin liquid phase that Kitaev had found, we found another spin liquid, which was actually a gapless spin liquid, and then you got into the conventional phase. So that was really exciting, that we are getting not just, there's sort of the richness here. There are many kinds of spin liquids. I've been talking about spin liquid as if it's one thing, but there are many kinds. And they, depending on the nature of the fluxes and the gauge theory, they can be gapped or gapless. So, okay, again, perhaps I should be ending now. So maybe just to show you that it's useful to look at different quantities, more conventional things. So this is the susceptibility, and you can see that this is susceptibility as a function of field. You're seeing two transitions. And the larger system you go to, the transitions get even sharper. So that's telling us that this result is for real. And you can look at spin correlations and so on. Okay, let me go to this crucial aspect of entanglement, which is what I started with. So entanglement is essentially, two qubits, it was easy to understand entanglement. Now I have many, many qubits. What is entanglement now? So what you do is you break up the system. Now we are looking at zero temperature, a wave function, and with that wave function, we can trace out so this can be the environment, and this is the system. So I can trace out this purple part and look at what the entanglement is between blue and purple using the density matrix. Okay, I'm skipping some of those details, but from the entanglement entropy and how it scales with the boundary, what you see is this is the expectation that there will be a boundary term, because that's where the system is entangling between blue and purple, but there is a reduction compared to that, which is coming from some topological order. Whenever you have order, the entropy is reduced. This is entanglement entropy, which has a reduction from the boundary term, and that is now a new order parameter called topological order. So that is something we could calculate here, and we could see that in the gapped spin liquid, it was log 2, and then when we entered this gapless phase, it increased beyond that because there were additional entanglements coming from the Fermi surface of gap Ranas. So that's very interesting. When we talk of Fermi surface, it's a surface for charge fermions. That's how we have understood Fermi surfaces for electrons. Here we are getting neutral Majoranas, and those are forming a Fermi surface. So these are very unusual states of matter where you're getting these organizations. Okay, I think let me end here. Let me end here. Just I'll flash this one phase diagram just to say I've kind of talked about, because I want to kind of get this message across to the students. We are often asking ourselves, some open problems. What are things we can do? So this is kind of useful to see how it all evolved with my students over the past just some few years. This is where Kitaev's solution had worked, and this was the field axis I told you about, where we went from this gapless to a small gap opening up to then the gap closing and giving us another gapless spin liquid here. The polarized states also turned out to be very interesting, and going off on some other axes here, where some of the bonds are made stronger than others, we found what we are calling the primordial fractional phases. Not just our string theory and high energy physicists should be allowed to call primordial soups, right? We also have primordial soups. So this is a soup here of gauge and matter degrees of freedom all mangled up together, and you can kind of access. What we found is actually if you, we always want to understand phases as some mother phase and other things emerging from that, and that is what we found. This is the mother phase, the primordial fractionalized phase with matter and flux degrees or gauge degrees of freedom, all of them entangled, and we could understand actually the Kitaev phase as a special case and all these other things as coming out of it. So I'll kind of stop here with this beautiful. I think it's beautiful because so much richness came out of such a simple Hamiltonian and some very beautiful physics that emerged out of it. So let me skip here, and I didn't have time to tell you about the materials, but there are indeed real materials and so on, which we can talk later. But I want to just end by showing my students who have done so much of the exciting work and hard work over the years on different aspects of this problem. Many of them have graduated, but this has been the group over the past, say, 5 years. So thank you so much for listening, and I'll take more questions.